Thank you and welcome everyone. So at Neral, we've built the first industry-grade tabular foundation model. And these past 2 years, you must have heard a lot about GenAI and how this foundation model were able to uh, generate an increase in efficiency in every team, whether it is to understand text, code, images, so whatever the data, at the condition that it is unstructured. But the problem is that most data driving daily decision in companies is structured in tables. More precisely, 70% of the value that is generated by a company is derived from the way they use the structured database. And if you want to use some language model, some generative foundation model to understand these structured databases, you won't be able to make prediction. And prediction is at the basis of most of machine learning use case in every company. So when you think about a recommendation system, a prediction model for churn revenue, to predict the number of people that will come to your stores, to detect fraud, all these models are based on classic machine learning algorithms that leverage unstructured databases. So you can try using some language model to make this kind of model and to predict some structured databases. But the only thing that you will be able to do is as descriptive statistics. That means you would be able to aggregate past information, for example, asking what was my revenue last year, but you won't be able to predict the value of a future variable. And this is exactly where the value lies. And this is what we are addressing at Neuralk. And for that, we've built a foundation model that was pre-trained on billions of tables and is able to understand the very logic, the very intelligence behind every system. It's able to predict, so classify, predict discrete labels, categories, predict continuous values, it's called regression, and even time series. So we call our model NICL for Neural Key Context Learner. And this model is able to make state-of-the-art prediction in a few shot settings, meaning that you don't need to retrain it on every table that you will get, like a data scientist used to do, but you just have to plug some contextual information to condition the model to perform the task. So I will describe it in more detail later, but basically let's start with the basis. So what is classification and what is regression? You usually start with a table, so a set of rows and columns. And the goal is to use a set of features, so a set of properties for different samples. Here you can see each line represents a product with the name, the price, the manufacturer, and you want to predict some labels. Here it's a discrete label, it's a category of the product. And for that, you usually split your data set with some training samples that will be used to teach the model to predict some new data, and the test samples, which are the samples for which you don't have the label, you don't have the information, and you want to predict it. So usually what a data scientist would do is to use these samples, the trained samples, to make the model learn, to learn the patterns between the name, the price, manufacturer, and deduce from that some categories. And with the approach that we've developed, you can see it similarly to what LLMs, to the way LLM functions. So basically, with the language model, when you interact with it, you prompt it. So you interact with natural language. You will give it some text, and this natural language will condition the model so that the model performs the task you want. But when you interact with it, you don't modify the weight. The model don't learn. It just uses the information as context. With our approach, you prompt our tabular foundation model the same way, but you don't prompt it with natural language. You prompt it with rows in a table. Basically, you can prompt it with some training samples, and these training samples will be used by the model to detect some patterns, some associations that will be used on the test samples, so the orange lines, rows, to predict in one pass, so without training. Thanks to our model, we can address a variety of use cases. For example, product categorization. So that's exactly the task that I was presenting before. Next best offer. So basically, you have an historic of product that were bought by customers, and you want to predict the next one that's going to be bought. So for that, you use the historic of product as a context for the model, and you try to predict what will be the next one. There is assortment recommendation, churn prediction, duplicate identification, and even fraud detection. So usually, here I go deeper into what data scientists used to do. They will start by receiving some data, and they need to extract some information from it before training a model. So they pre-process it, they input missing features, they try to remove some outliers, scale numerical features, project text into a space with numbers. So this is the feature engineering part, where you try to extract the information from your original input to give it to machine learning models that will learn some patterns and do the prediction afterwards. But to be able to extract the meaningful information from your data is quite difficult. It requires expertise. And there is a lot of iteration between your data and your model. So usually data scientists will start to do some feature engineering, train a model to get some feedback about the quality of the signal it was able to extract. Usually you have some poor performances at the beginning, so you modify your feature engineering, you train another model, you evaluate it, and you do it all over again for a few dozen of iterations. It takes time. Then, once you're happy with the model you have, you deploy it, and then you can use it in production for inference. But data and customers' behavior can change through time, so you need to monitor the performance of your model. At some point, for example, when you have some recommendation system, the customers won't buy the same product, they won't behave the same. So you will see the efficiency of your model decrease. At this point, you need to do it all over again. So it's quite cumbersome. And thanks to a model, there are two advantages. The first one is the data scientist efficiency, because there is no more model training. So you don't have to wait between each iteration between your data and your model. You just have to do your feature engineering and send it to the model. And in one pass, so at inference, you get your results. It's almost instantaneous, and then you can run your whole list of ideas in one day, while it will have taken like a few weeks to test everything, or a few days. Then there is the operational efficiency. No more complex deployment, where you have some complex CI/CD pipeline, some monitoring and some retraining on your model. We can just have some managed inference endpoints and use the same model for all your use cases. Basically, if you had 100 models for 100 use cases, you just have one model remaining. And the nice plus is that it's robust to data drift. So basically, as you control the behavior of your model using the prompt, so using the line of context, you can just adapt your strategy. It's like when you do some prompt engineering with a language model, trying to define the best prompt for the task you want. With our model, you can define a prompting strategy, meaning, for example, I want to use, let's say you want to predict some product that will be bought by a customer. You might want to use the last 10 products that the customer bought as context, and use this information for the model to predict the next one. And so by giving just this rule, just this context strategy, you can have a model that is robust to data drift, and avoid retraining and reworking on your data later, like you used to do with classic machine learning. And finally, the last and most important improvement is the performance. We get state-of-the-art results, and so whether you are a good or less good data scientist, you'll still get excellent results. We have some benchmark that you can check if you want to have a look at the performance of our model compared to other approaches on a set of academic and industrial data sets. We compare our performance to other approaches, and so the accuracy, the efficiency, as well as the scalability of the model. Our model is quite efficient in terms of latency and in terms of scalability, using some clever tricks, I would say, regarding information compression. We're able to scale it drastically and be able to address real use case problem where other approaches are stuck to academic data sets. So next, I'm gonna do some risky live demo. You can access an API. So we deployed our inference server on the Scaleway GPUs. And if you have some computer right now, you can, or if you have a computer at home, you can maybe try later. I think the server will be down tonight. So your time is counted. But you just have to go to this address, fill the form, and then you can access a Colab notebook to interact with our inference server. And basically, you can use it the same way you would use a machine learning model. I'm gonna do the demo live. We prepare some the Colab notebook with some examples, some tools to pre-process the data. And if you don't have your own data, you can just load or generate data sets. Can you see the screen at the end of the room? So basically, so people that are not used to code, it might be a bit obscure at this point. You start like all data scientists will always start. You just import some packages that are libraries that are used to perform some functions. Then we load a dataset. So this is an academic dataset. Basically, it's a set of numerical motion extracted from 7 videos of people gesturing. So you have velocities, acceleration, and risk coordinates. Basically, the idea is to predict the gesture phase based on the motion features. The dataset has almost 10,000 features, lines, so samples, and 32 features. We can have a look at what it looks like. Basically, this is something like that. So a classic data set, sorry, with features, numerical features. You get some idea of the range, unique value, so no missing value. Just to compute. So you get an idea of what we're dealing with. And then what we do is what usually a data scientist would do is to get some data to train on and some data left to evaluate the performance of the model. So we have this X-train, X-test. So basically the sample that I use to train the model or a classic model or use as a context for our model. And some sample on which you want to make the prediction. Here we just wrote some pre-processing tools to prepare your data. Depending on your data set, you can modify it to match your needs. And then in just 3 lines, we're able to connect to the server, to contextualize the model, and to make the state-of-the-art prediction without having a super complicated optimization of the hyperparameters, which takes time, which requires a lot of expertise because you can be stuck in the local optima. And one of the advantages of the architecture that we've developed that it's much more powerful than classical machine learning algorithm, because XGBoost, CutBoost, LightBoost, Random Forest, they all support that your data is that your sample, sorry, is what is the word? Independent, sorry. While our approaches, it takes into consideration the interaction between samples. So it takes the information that's derived from the interaction between features, but also between samples, so between rows and between columns. And here, you can see just connecting, contextualizing, and predicting and evaluating. So instantiating, contextualizing, and predicting has taken like a second. And we have a quite good performance of almost 80%. And then what we do, as you see, it's a bit more complicated. we just instantiate XGBoost models, the classic model that is used in like 80% of the company that do machine learning. And I launched it and it's still running. And it's simple to use, but complicated to optimize and to reach perfect performance. As you can see, it has just finished, a bit longer, and with 10 point of accuracy below what we were able to achieve. So you can find also in the Colab notebook a set of documentation and access to the API documentation and information about how to use our model and how to optimize its performance on your datasets. And you can also find this Colab on our GitHub. There is a AI Pulse workshop 2025. There is another one for last year workshop. And that's it for today. So if you have any question on the web, I think we have a few minutes. You can ask them. If you want to get access to the API, I invite you to go to our website and to request access. We'll give you free credit to experiment with it. So feel free to ask for access. Thank you.
How the model deals with new labels and new products? For example, when you have a recommender system and you provided as a context some data from previous sales, and suddenly at one day you launch a new product.
That's a good question. So if it's a new product, there is no issue because your product will be represented by some name, by some attributes, features that are going to be used by the model to predict the label. But if you have new labels, so new point in the space in which you're trying to predict, then indeed you have some issue because the model doesn't know that this new point exists. And the way we do it today with our customers, that we try to build this human in the loop, this augmented data scientist in the company. For example, with Saint-Gobain, we were able to achieve like 98% accuracy on more than half the data set. So that means that half the data set can just go into on the website, ready to be sold directly without the intervention of a human. And for the rest, what we can do is just give the top K prediction for the human annotator to just be super efficient and choose accordingly. In addition to that, we have some probability, some uncertainty given by the model on age prediction. So we have designed some process to cluster products based on this uncertainty. Usually, if you don't have this label that has just been created, you will get a high uncertainty of the prediction that was made. So we give some feedback to the team of our clients with the prediction that are made for them to identify, for example, that a supplier didn't give them a lot of information or get really bad product data. They can have a nice feedback loop with the supplier to teach him to better fill the product card, or we can introduce some new context into the model for the next time.
Yeah, quick question. Thanks for the demo. It's cool. So that demo was on numerical data only, right? Or was there text data into the...
No, we work on text data, especially for product categorization, where most of the data is textual.
Right.
But the model process numerical information, like even language model, the process numbers. You just have to vectorize it, project your text into this latent space of numbers.
Yeah.
And this is exactly what we do.
And for the demo here, like, did you perform any normalization on the numerical values themselves, any pre-processing like that, or?
Usually what we do is that we scale the data, we remove some outliers, and that's it. Super minimal pre-processing.
Just basic scaling and other, okay.
But the way we recommend to use as you've seen, this is just the access to direct access to the model. with clients, we've been building around this model to help them scale it and adapt it to their business knowledge. Basically, trying to understand the limitations, the high space of categories in which we're trying to predict. So we were the one to build around it. But for teams that have already some knowledge that they acquired during 10, 20 years, and for which it will be complicated for us to teach them things about how to extract information on the data, we prefer to let them build on our model. So basically, they have the business knowledge, they know how to extract their information, and they will be the one to find the best context to use combined with our model.
Yeah, makes sense. Thanks very much.
Thank you.
Thank you for the presentation. I wanted to ask you about you said that the difference between the machine learning algorithms and ROC is that machine learning algorithms handle the samples as independent. How do you do to handle this correlation between samples? Do you use some kind of attention or something like this? Thank you.
Yes, you answered the question. Yeah, we do. We have some attention mechanisms, like in transformer-based architecture, and so this is how we were able to leverage interaction between samples and features.
Hi, I was wondering if we want to test it on a use case that we have, but we would just want to benchmark it very quickly to see what the results are, if they would be interesting to investigate. Is there an open endpoint we can have, even with like high latency or something like that?
Yes, you can go to a website, request an API access, and we'll give you free credit to experiment with it.
Hi, thank you. Great presentation. You mentioned limitations. Could you zoom in a little bit of limitations that your customers discovered or that you discovered, like use cases that your customers were considering it might be possible and then you were advising not to go there?
So the main limitation that we have set so far is when the customer doesn't have the data infrastructure ready for this kind of prediction system. So basically, if you don't have data or if your data is not qualitative enough, there will be some issue. This is the biggest problem we've seen so far.
What are the limitations that you...
In terms of model, in terms of the architecture, so we're able to scale to millions of rows. This is something that we keep working on. We want to be like agnostic to the size of the model or the datasets. Yeah, this is a constant marathon for more performance, less latency, and more scalability.
Thank you, Alexandre.
Thank you.